So in my last two videos, we've been talking about Gauss's law and charge distributions. And what I want to do in this video is try to show how the whole process that I outlined in one of my earlier videos about how you could solve any electromagnetics problem in principle by breaking it up into little cubes and finding the net charge in each little cube, treating each little cube like a point charge, and then integrating or summing up all the contributions of the fields. In principle, you can solve any electrostatics problem with that. But I want to show how all of this information is embedded into Gauss's law, this simple, elegant equation, del dot D, or the divergence of D, is equal to rho V. So I showed in my previous video, I kind of explained intuitively why this is true, but we didn't go into how do you get like the equation for the fields from a point charge from this. And so I want to show that to you in this video. So what we have to do is we have to apply the divergence theorem to Gauss's law. So if we integrate del dot D over a certain volume, using Gauss's law, that should be equal to the integral of rho v dv, which this whole expression here, this is coulombs per meter cubed times meters cubed, that gives us the total charge within that surface. So what we can say is that Q total is equal to the integral of d dot ds over the whole surface, or the flux going out of the surface. So let's think about how we can apply this to a point charge. First, we can form a surface around the point charge here. I'll go ahead and do a spherical surface. And Gauss's law says that the integral of d dot ds is equal to the charge Q enclosed in this surface. So one thing I want to make note of is that because this is a perfectly symmetric problem, the field has to be radial or spherically going outward due to symmetry.
You mean what? You look like an egg, or like a little loaf. Are you a loaf? A bread loaf?
Now, to evaluate this integral, d dot ds, because the field is already perpendicular to the surface, this integral just simply comes out to the magnitude of d times the surface area of a sphere, which is 4 pi r squared. And that should be equal to q. So then you can rearrange and solve for d. And that then means E then is equal to q over 4 pi epsilon 0 r squared. And that's because d is equal to epsilon 0 e. And notice that this is the field from a point charge. So that's how we get the field from a point charge using Gauss's law. Now you might be wondering is, where do we get this whole idea of superposition from Gauss's law? And the way we get superposition is, I want you to think about what type of equation this is. If we expand this, it's del dot D here, we get this equation here. And I want you to notice that this is a linear differential equation. And mathematically, if it's a linear differential equation, then if you have one solution to the equation, and then you have another set of solutions to the equation, then the sum of these two solutions, d1 plus d2, and rho v1 plus rho v2, is also a solution. And so that means that essentially embedded in this equation is the principle of superposition as well. So I think this is really cool how, this elegant expression really just describing this idea of breaking a problem up into these little point charges, finding the fields from each little point charge, and then applying the principle of superposition to find the total fields. For those of you watching these videos and you're not in my electrodynamics class, you'll notice that these videos are pretty conceptual, and I am using them to kind of supplement the examples I'm working out in class. And that was basically due to the fact that I found out that I was just getting too busy to make so many videos. So if you are going through this series and you're not in my class, I think what these videos are good for is kind of helping you step back and really understand the concepts. But I'd highly recommend you check out like a good electromagnetics textbook where you can really work through some more mathematical examples. And eventually, someday I'll probably upload more videos where I'm actually working out concrete mathematical examples. But anyway, hope you are enjoying the series, and I will see you in the next video.